or which can also be considered as the properties of shortest path, and so as some properties of Dijkstra's algorithm. So as part of these theorems, we are going to eventually prove what is called the correctness of this algorithm. So when I say correctness, it means that we are going to show formally that this algorithm is working correctly and will always find the shortest path weight for a given graph. So that's how we prove the correctness. So as we did for the Kruskal's algorithm for minimum spanning trees, we have to prove kind of more formally without picking a specific graph. We have to prove in general that this algorithm is going to find you a shortest path for any arbitrary graph. Again, remember an important assumption for Dijkstra's algorithm: the graph should have only positive edge weights, means edge weight should be greater than 0. So we'll make use of this as we prove the correctness of the algorithm. Okay. So we are going to see like four theorems. So each theorem, as we move on, will build on the earlier theorems. So we'll start with a simple one, that the subpath of a shortest path is also a shortest path. So this is actually like a property of shortest path, and I did mention this last time. So what it means is, when you have, say, a path from S to D, and let us say this is the shortest path between S and D, and the weight is like 5 plus 3 plus 2 plus 4, which is 14, is the shortest path weight from S to D, and this is the actual path, like S, A, B, C, D. Now every subpath of this shortest path, okay, so given that this S, A, B, C, D is a shortest path, every subpath of this shortest path is also a shortest path. That's what is the property. Now how we prove this? We can prove by contradiction. So let us pick this pair A and C. So according to this, so given that SABCD is the shortest path, let us say ABC, which is a subpath, is not the shortest path. That means there exists some other path from A to C. So the numbers is just for example for me to explain you guys. So you can do all these things without giving any specific numbers. Okay. So let us consider alternate path from A to C that is actually the shortest path, which is like a hypothetical path. So let us say there's a hypothetical path from A to C other than ABC, whose path weight is less than the path weight of ABC. Like in this case, the path weight of this hypothetical path is 1 plus 2, 3, and less than the path weight for ABC, which is 3 plus 2, 5. Now the question is, can such a hypothetical path exist as a shortest path other than this subpath from between A and C on this path? Why? Because we are given that SABCD is the shortest path. That's given, and what we are claiming is one of the subpath like this ABC is not a shortest path. Can that be possible? The answer is no, because if there is a hypothetical shortest path between A and C of weight less than what we have as part of this shortest path from S to D, then as you can see in this figure, we can make use of that hypothetical path and go from S to D, and that would actually eventually reduce the path weight from S to D from what we know currently. Because if you use this hypothetical path, it will be like 5 plus 1 plus 2 plus 4. That will be like what, 6, 8, 12, less than 14, because we are going through a better path from A to C and then to D. So that means SABCD is not a shortest path to begin with. But remember, we are given that SABCD is a shortest path, and we are claiming that for a pair AC, okay, so that's a subpath ABC is not a shortest path, and we are claiming that exists a hypothetical shortest path from A to C other than this ABC. And what we are now proving or showing is such a hypothetical path cannot exist, because if such a hypothetical path exists as a shortest path between A and C, then SABCD itself is not going to be a shortest path. So in this example, it's going to be SAKCD is going to be a shortest path. That's like a contradiction. So in order for SABCD to be a shortest path, every subpath of it should also be a shortest path. If any subpath of this shortest path is not a shortest path, then the original path itself is not the shortest path. So that's what we are proving. Okay, so you can type if you have any questions. So that's an important property. Every subpath of a shortest path is a shortest path. So let us now move on to the second theorem. So, and this is going to be all related to the working of the Dijkstra's algorithm. Now let's go back to the example that we just saw, or any example that we saw for the Dijkstra algorithm. Now if you look at the numbers, the estimated shortest path weights of the vertices we are picking as being optimized. We pick one first to begin with a 0, then 3, then we pick 4, then we pick 6, then another 6, then 9, right? So 0, 3, 4, 6, 6, 9. That's a sequence of values. So what is the sequence? This is in increasing order. Okay, so that's the theorem. The weight of the vertices that are optimized are in the non-decreasing order, that is typically increasing order. So why it's more general to say it as non-decreasing rather than increasing is, like even in this example we just saw, the sequence is what? 0, 3, 4, 6 followed by another 6. So if you say increasing, it should be just increasing. No two values should be the same. So a better way of referring to such a sequence where some values could be repeated is called a non-decreasing instead of telling increasing. Both mean the same really, but if you have more than one instance of same value, then we can say it's non-decreasing instead of just saying increasing. So that's the property of the Dijkstra's algorithm. The shortest path weights of the vertices that you are considered to be the path weights for the vertices that are optimized or in the non-decreasing order. Now how can we prove this? Okay, so let us consider a vertex u that we optimize in some iteration I. Okay, there's another vertex v that was optimized in a later iteration j. So I is less than j. So I is an earlier iteration, j is some later subsequent or some other later iteration after I. Now what we have to show is the estimated path, shortest path, not estimated, the actual, the optimal shortest path weight from S to U, we'll refer it as weight of U, is always going to be greater than or equal to the weight of V. Sorry, the other way. This is a vertex u is a vertex that was optimized in the earlier iteration, right? So its value is always going to be less than or equal to the estimate, the path weight, shortest path weight of a vertex v optimized in later iteration. So that's what I'm telling weight of v is going to be always greater than or equal to the weight of u, because u was optimized earlier. So since u was optimized earlier, it's going to have a smaller path weight compared to v. So a vertex that was optimized in a later iteration is always going to have greater than or equal to the estimated shortest path weight for a vertex that was optimized in an earlier iteration. Okay, so that is the sequence, because you see in the example it is like what, 0 for A, then 3 for F, then 4 for B. So the shortest path weight for B, which is 4, is greater than the shortest path weight for F, which is 3. Then the next iteration optimizing D, the shortest path weight is 6, which is greater than the shortest path weight for B or F. The further iteration you optimize E, the shortest path weight is 6, which is greater than or equal to that of D or greater than that of B or F. Similarly, the last iteration you are optimizing C, the path weight is 9, which is greater than everything that was optimized earlier. So that's the theorem. So how are we proving this? We are going to pick two vertices u and v such that u was optimized earlier in some iteration I and v was optimized later in some iteration j. Okay, So what we are going to show is the weight of v is always going to be greater than or equal to the weight of u, the path, shortest path weight. Alright, so we are going to look at two scenarios for this. This v that was optimized in a later iteration could be a neighbor of this vertex u that was optimized earlier. Or v need not be a neighbor of u, it could be a neighbor of some other vertex x. Okay, so we have to deal with these two scenarios. Now again, in this earlier iteration I, in which we optimized u, we picked u and say we have said that we optimized u because among all the vertices that were not yet optimized, u had the smallest shortest path, estimated shortest path weight. That's why when we dequeued the q, u came out of the q and we said that we have optimized u, right? So again, if you go back to the example, when we pick this 4 among 4, 11, infinity, infinity, 4 is the smallest value, and that's why we claim we optimize this vertex b. So that's what we do in each iteration. Among all the vertices that are not yet optimized, we pick the vertex that has the smallest estimated shortest path weight and we claim to have optimized that vertex. That means to have found the shortest path weight for that vertex. So when u was picked up for that iteration I, that means u had the shortest path weight among all the vertices but are not yet optimized. And one of that non-optimized vertices is also v. So v had a shortest path weight that was greater than or equal to u in iteration I. That's why we picked up u instead of v, right? So u had a smaller shortest path weight than v, that's why we picked up u and say we optimized u. And what we could have done as part of this optimization, we would have relaxed the neighbors of u. So if v is a neighbor of u, we would have tried to reach v by going through u and reduce estimated path weight of v. So how we would have done this? So if let us say there is some path from s to v, by going through u, we are going to see if we can reduce the path weight for v. So the weight of the path from s to u, which is this weight of u, plus the edge weight uv, is the sum going to be less than what we know currently? That's what we are going to check. And if we are able to reduce it, we are going to change the weight of v. But remember that new value for the weight of v is still going to be greater than the weight of u, right? Because every edge weight is positive. So think about these numbers here, like this case. So we this is f is say our u. Now relax the neighbors of f, which is say b. So the current estimated path weight for b is 5. And now by going through f, we are trying to see if we can reduce a path weight for b. So what we do, we say 3 up to u plus edge weight 1 is 4 less than 5. So we make this 4 and make u as a predecessor or f as a predecessor. But remember, this 4 is still greater than 3, right? This 5 was greater than 3. And after the relaxation step, what we have, the path weight for b is still going to be greater than the path weight for f, because all edges are going to have positive edge weights greater than 0 weight. So even after the relaxation, the estimated path weight for v is going to be only greater than or equal to, at the worst case, the weight of u. It's not going to become less than the weight of u, because what we want to prove, the shortest path weights of the vertices that optimized are in the non-decreasing order. So if we end up optimizing v in a later iteration, after iteration I, the path weight for v is going to be only greater than or equal to the path weight of u that was optimized in the ith iteration, the earlier iteration. So this is if v is a neighbor of u. Now the same logic can also be used if v is not a neighbor of u but a neighbor of some vertex x through which v gets optimized. Okay. Now again, in the ith iteration, x is not yet optimized. So that's what we are assuming here, because if we are claiming that when u is optimized, v is not optimized, right? So if v is not yet optimized at the time of u getting optimized, then a neighbor x of v should also not be optimized, because if x was optimized, we could have relaxed the neighbors of x, and v could have had a smaller weight than u. The reason we say vertex v is not yet optimized when time u is optimized is a neighbor of v is also not yet optimized, right? So let us pick one such neighbor of x that is not yet optimized. So now the weight of x is greater than or equal to the weight of u, because u was picked ahead of x. Okay, so if that is the case, in iteration I, u was picked ahead of x, and v is going to be optimized through x, the weight of v in the ith iteration will also be greater than or equal to the weight of x, which is greater than or equal to the weight of u, the ith iteration. Now this is an ith iteration, the earlier iteration. Now in the later iteration, let us say x got optimized. Now since again we just proved that the weight of x was greater than or equal to the weight of u, and all the edge weights are positive, even if x gets optimized in a later iteration, the weight of x is going to be still greater than the weight of u. So now when relax the neighbors of x, again since all edge weights are positive, the weight of v is still going to be greater than or equal to the weight of x, and which is again greater than or equal to the weight of u. So even in a later iteration, if v gets optimized through some unoptimized through a vertex x that was not optimized when u was optimized, the weight of v is going to be still greater than the weight of u. So that's how you prove. If v is not a neighbor of u, its weight at the time of its optimization is still going to be greater than or equal to the weight of u. Okay. So let me save these two videos and